Hi, everyone. Thank you for coming. I'm Ben. The work I'm about to present is joint work with Josh at UMD, Siyuan and Xiaokang at Purdue, Vu at UNL, Jeff at Tufts, and Armando at MIT. So what's our goal? Our goal in this work is to support general-purpose sketch-based synthesis of Java programs. So what do I mean by that? Well, the inputs are Java programs with some unknown values, along with a specification using Java code over quantified arguments, which will constrain the possible values for these unknowns. So our outputs are going to be a Java program with satisfying assignments for these unknowns in our program according to the specification. Okay, so let's take a look at a kind of simple example that we're going to use for this talk. So here on the left, we have our Java program with unknowns. This is a Java method that's going to compute the intersection of two arrays of integers A and B. So how's it going to do this? First, we declare a set of integers. We're going to loop over the A array. Then we're going to loop over the B array. And finally, we're going to compare elements of those two arrays and add them to this intersection if they're equal. So you might notice there's some things in here that are not standard Java. In particular, there's this question mark syntax, which refers to a hole, which is supposed to be filled in with some unknown integer value. And then we have a generator, which is going to represent a choice between multiple possible expressions. So you'll notice for our entire sketch, this Java program with unknowns, we're going to use unknowns here for the guards to these two for loops. Additionally, we're going to use a generator for the comparison of these two elements of these arrays. So that's our Java program with unknowns. And on the right, we have our specification. So what's this going to look like? So first, we're just going to use this harness keyword to indicate that this is a method that's supposed to specify what the Java program on the left is supposed to do. Additionally, when we pass these arguments to it, we're indicating, because we use this harness keyword, that these arguments are universally quantified. So these are universally quantified integers in this case. So how are we going to actually use this to specify what we want the program to do? So we're going to use assumes and asserts. In particular, the assume here is going to put some restrictions on these universally quantified arguments. So it's going to restrict them to be ordered, and this will mean that they're unique elements. We're going to declare two arrays, A and B, over these universally quantified arguments. We're going to call the intersection method on A and B. And then finally, we're going to make some assertions about what this intersection should do. In particular, we're going to assert that the intersection should contain the elements x and z, and that its size should be 2. OK, so let's state the synthesis problem a bit more formally. So what this is saying is that we want to ask the question, does there exist an assignment of the unknowns in the program on the left to real values, which we'll call h, such that for all possible values of w, x, y, and z, we satisfy the assertions in the specification on the right. So there's kind of a difficult problem here, hiding in plain sight, and that's the following. Is how should we reason about the semantics of this library we use, in particular this set library? So you'll notice we call the add method along with contains and size, and we need to know what the semantics are for this in order to properly synthesize values for the holes in the program. OK, so what are some possible approaches for doing this? One is to find the source of this library and just concatenate it onto the input sketch and feed that all to our synthesizer. But there's some problems with this. So often, especially for Java standard library source code, there's lots of code with huge webs of dependencies that are going to be difficult for a synthesizer to reason about. And additionally, it might support native code, which are going to be difficult for the synthesizer. So a second approach would be to create a simplified Java implementation, which we're going to refer to as a mock. So what this would really mean would maybe we would look at the source but realize it has these problems, and so we would create our own simplified implementation. So this could work, but it also has some potential problems. So they could still be large and complex, and in particular they could be because they might include unnecessary implementation details. So an example for the set that we're talking about is if we decided a natural decision might be to use an array to store the elements in this set, but Java arrays require you to declare them with a fixed length, whereas a set should be able to have an arbitrary length, And so this might require us adding in code, dynamically resizing this array on the back end. Okay, so our idea is to model library semantics instead using algebraic specifications. So what do we mean by this? So algebraic specifications for us are rewrite rules of the following form. So on the left-hand side, we're going to have a sequence of method calls. And on the right-hand side, we're going to have a result. So let's show you an example for the set class we're talking about. So in particular, how we can read this rule is that if we create a set with the empty constructor and then ask if it contains some element E, that's always going to evaluate to false because it's an empty set. So you'll notice here that this, the notation we're using here is that this first argument is actually the receiver. And so when we're reading this, we can kind of read it from the inside out. In other words, first we called the set constructor, and then we asked if it contains this element E. Okay. So throughout the rest of the talk, I'm going to describe in more detail how we can model some of these libraries using algebraic specifications. I'm going to describe how we can integrate these specifications into the synthesis process with our tool JLibSketch. And finally, I'm going to show how it fared when we evaluated it on 9 programs from 3 different domains. Okay. So let's take a look at some more examples of how we can algebraically specify this set library. So I've already shown you this first rewrite rule here, but here's a second rewrite rule. And what this rewrite rule is saying is if we have some set S and we add an element E2 to it, and then if we ask, does that set contain the element E1? If E1 is equal to E2, then yes, it does contain the element, return true. Otherwise, recursively look in the set S to see if it contains the element E1. And you'll notice here that we use this exclamation mark notation. And what that's referring to is actually the state of the set after the call to add, as opposed to the actual return value of the add method. Okay. So really quickly here, I'm going to show you we actually provide a nice syntax for users to be able to express these in a sort of Java-like way. I'm not going to go into too many details, but essentially we use some annotations here to indicate that a class actually allows for algebraic specifications and which methods we're going to algebraically specify. And then at the bottom here, you can see that we provide a kind of almost Java method-like syntax for expressing these. But there's more information in the paper if you're interested. Okay, so kind of the big question is how do we actually integrate these algebraic specifications into the synthesis process? And we should kind of keep in mind that we need to support sketch-based synthesis with these universally quantified harnesses like I showed you before. So how do we achieve this? So recall the inputs to our system are going to be the Java sketch, which is this Java program with unknowns, the specification, which was that harness method, and additionally some are representation of the libraries using these algebraic specifications. And we're going to solve this by translating all of these inputs into a sketch file, which is going to be fed to the sketch program synthesis system, which is a well-known system for doing this, which works by converting this into a SAT formula. It will find satisfying values for our unknown assignments, and finally we can plug those back into our Java program and have a complete Java program that satisfies the specification. Okay, because Sketch is kind of is an existing system, we're going to focus on the translation from our inputs into Sketch. If you're interested in Sketch, I encourage you to check out the manual and other related works online. And actually, in particular, we're going to get a little more focus here on the translation of the libraries into Sketch, because the translation of both the Java program with unknowns and the specification are fairly straightforward. For instance, methods in the Java sketch will become functions in Sketch, and the harness in the specification will just become a harness in Sketch. But there's definitely more information about this in the paper if you're interested. So how do we actually translate these libraries? Well, you recall we have these sequences of method calls, which is the left-hand side of our rewrite rule. And we're going to represent these using ADTS. So in particular, each of these 5 elements is going to be a constructor. The first is going to represent the empty set, so it takes no arguments. And the second 2 are going to be our add and add bang. So we've already seen the add exclamation mark, which indicates the state of the set after a call to add. And the first one is just what I told you about, the actual return value of the method. So you'll notice for contains and size, there's no exclamation mark methods. This is because they don't affect the state of the set. Okay, so let's take a look at an example to see how this works in practice. So on the left, we have JLibSketch code, and on the right, we have sketch code. So you'll notice we declare a set on the left, and it just becomes the identical code on the right. But on the right, keep in mind, now we're dealing in the domain of abstract data types in Sketch. Okay. So now we add two elements, E1 and E2. And you'll see on the right, this becomes two different constructors of new ADTs on the right using this add bang constructor. And finally, we're going to have a call to ask if it contains the element E1. And this is translated fairly straightforwardly into the sketch as a function call. So the question is how should this contains E1 actually be evaluated? So now the sketch code is on the left. In the orange box, I've just rewritten the algebraic specification I showed you before. And this term here actually is pretty much identical to the sketch code. So recall we read from the inside out. So this means first we constructed a set using the empty set constructor. Then we added an element E1. Then we added an element E2. And finally, we asked, does this set contain the element E1? So you'll notice, if we pretend this piece I just highlighted in green here is the S from our rewrite rule above, this is identical to the left-hand side of our rewrite rule. So we're going to apply it and ask, does E1 equal E2? In this case, we're going to presume that they are not equal. So it's not going to evaluate to true. Instead, it's going to evaluate to a call to contains of this inside piece, which we labeled in green. So indeed, it becomes that. We notice that this, again, is the same form as our rewrite rule. So we're going to apply the same rewrite rule again. We ask, does E1 equal E1? And this time, we're going to presume it does equal itself. And so we get true. So this is the semantics we expect for these rewrite rules. How do we actually do that in Sketch is the question. So on the left here, I've just repeated the algebraic specifications we've seen before. And we translate these into Sketch using a recursive function. So in particular, you'll notice there's two arguments. This is the contains function we've seen before. The first argument here is the ADT representing the sequence of method calls that we've seen. And we're going to use this switch statement to look at the outermost constructor in this list, this sequence of method calls, and apply the appropriate rewrite rule, which you can see translated almost directly into the sketch code. OK, so that's kind of the high level of how our system works. How did we actually evaluate it to see if it's any good? So we chose 9 benchmarks from GitHub with libraries from 3 different domains. So in particular, data structures, cryptography, and file manipulation. And these range from 200 to 500 lines of code. The problem is obviously these are complete programs. So how did we turn these into synthesis problems that we could evaluate on? So we applied a systematic approach for introducing holes and generators. OK. So on the left here, you'll see one of the benchmarks from our evaluation. The details here aren't too important, but what you should notice is on the left, there's a function called LRS. And it does some complicated things, like it has 2 different loops and some complicated looking guards. And this is going to get translated into this big thing. But the things you should focus on is, so here you have this assignment to this character array temp. And that is going to get translated into this call to statements, which is actually a recursive generator, which you can think of as generating possible statements that could be put here. And the space of possible statement that this could produce is quite large. And we do a similar thing for the guards, where now instead of producing statements, we're producing Boolean expressions that we could use for these guards. So the high-level takeaway of what's going on here is that we have a systematic process for developing quite challenging sketch-based synthesis problems for Java, which are going to be our benchmarks on which we evaluate. OK. So here is part of our results. So on the left, in the left-hand column, you can see our benchmarks, so 9 benchmarks from GitHub. And here in this table, we're going to compare how many lines of code did we use to write the specifications, these algebraic specifications, versus these mocks, which you'll remember are these simplified Java implementations. So indeed, this first column here is the lines of code we use for the specifications. The middle line is the lines of code we use for the mock. And the last column is the ratio of lines of code we use for the specifications versus the mocks. So in particular, the kind of high-level takeaways of this graph, or this graphic rather, are, first of all, the specifications were always shorter than the mocks, which kind of makes sense. These are a rather declarative way of expressing the semantics. And in particular, actually, on average, they were about half the lines of code. So these are going to be a shorter way to express the behavior of these libraries. OK. Perhaps in my opinion, the more important result here, so this is performance in terms of how long did it actually take to synthesize the correct result. So again, on the left, you'll see our benchmarks. This middle column here is the median time it took the synthesis problem to solve using the mock representations of the libraries. We take the median because there is some non-determinism in Sketch. So we actually ran each of these 31 times and took the median result. And the right-hand column is the algebraic specifications, the time it took to run with those instead of the mocks. OK. So let's notice, so on 7 of the 9 tests, the algebraic specifications performed significantly faster, significantly in a statistical sense because we use the Mann-Whitney U test to compare these. You'll notice in particular, so the TO in this table is a timeout, which was 4 hours. The results are in seconds, so 4 hours is like 14,400 seconds for reference. So actually, in the best case, we solved in around 3 minutes, whereas using the mocks took at least 4 hours. It timed out. And to go back for a second, the two problems, or the two benchmarks rather, where the algebraic specifications did not do better, it's not necessarily that they actually did worse than the mocks. It's just that neither was able to be proven to do statistically better. So you can actually see for the second hash map problem, they performed exactly the same. And for the ROM list benchmark, the algebraic specifications performed faster, but not statistically significantly so. OK. So to wrap up, we introduced algebraic library specifications for modeling this library behavior for synthesis. We provided this translation from these algebraic specifications into the Sketch program synthesis tool. And we assembled 9 Java benchmarks to test this approach. And we found that specifications were on average much shorter than mocks, and that they performed significantly better on 7 of the 9 benchmarks that we chose. So thank you, and I'm happy to take questions.
Well, I have a question. Sure. So the algebraic specifications that you're using look syntactically very similar to the ones that Divan and Henkel were using in their algebraic specification discovery tool, which you also cite in your paper. So I'm curious, did you think about, or did you try using their tool and see if there are similarities in the handwritten versus the automatically generated specifications, and or whether you could use this tool to automatically generate what you're looking for?
Right, that's a great question. So no, we didn't look at doing that. I think it would be a very interesting thing to do. And in particular, I think that's one of the benefits of algebraic specifications versus mocks, is that I think there's an argument to be made that, at least for some of these libraries, automatically generating these specifications is definitely possible. And it makes this an even more attractive approach because now the user doesn't need to write these specifications, but they can be automatically generated. Yeah. Yep.
Any questions now? Well, looks like we are very good on time. Actually, I'll ask a question.
Sure.
Okay, I think now it's on. Yeah, so just looking at the beginning with the examples of the sketch, I'm just very curious, like how in practice, how useful do you think this will be? Because like your example with the set intersection, that seems like a bit of a toy example where
Yes,
there's
very much so.
less code to just write the thing yourself. I'm curious, like
So I mean,
applications.
I guess it depends, right? I think so. Sketch-based synthesis to me seems like a promising approach to this problem, because typically, if you're trying to synthesize a whole program from scratch, that's not going to be feasible in a lot of cases, especially just for like general purpose synthesis. You're right. This is kind of a toy example. Like, it would be surprising if someone didn't know how to correctly like initialize those guards to those loops. But in practice, I think there's a lot of instances where the sketch-based synthesis approach can be really valuable. Some of them that have been in the literature before have been like kind of strange manipulations for like Boolean operations, where you can kind of have optimizations that are equivalent but not necessarily very intuitive. So that's like one example. But I think there's a lot of places where you might know the structure of the code that you want to write, but there are some specifics that you don't know how to do. So like another example might be dumb like off by one errors in guards to loops and things like that.
I'm curious too if like functional programming it would potentially, I don't know, do you think this would be applicable?
So you mean the use of these algebraic specifications to represent libraries? So, I mean, you'll notice that this already kind of looks functional, right? Like, so yes, I think you could use these with like a functional program when you're synthesizing functional programs. In practice, do I think this is going to look a lot different than the mock you're going to write? Maybe not, because they're kind of already functional in style.
Right.
Yeah.
Thank you.
Yep, thanks.
Let's thank Ben again.